All right. So with this next section, I want to sort of introduce us to sintering and the mechanisms that are occurring throughout this process. So the first thing is we've talked about the act of sintering and the furnaces and the heating elements that we can use, and we've talked about sintering or firing in the lab with the superconductor lab. So there can be multiple program segments to sintering, and sintering is just one of the parts that may be useful in that process. So I've kind of put up a multiple stage process that involves sintering, but also has some other features in it as well. So the first one we've talked about before, we often have to do a heating treatment to burn out any binders or plasticizers that we've added along the way with shaping. And so that can be added here. And so that's, like I mentioned in those lectures, is typically a very slow heating up to about 500 degrees. And then hold there for a couple hours. And this allows us to get all those organics and get them slowly out so that we can get rid of that empty space left behind. We can also do, there's often other types of things. A low temperature soak might be used in conjunction with the burnout. It might be used for thermal shock and so forth. So there's lots of other reasons to have that. But then typically we're going to heat up to the sintering temperature. And we typically do an isothermal sintering. So this means that we do it at one temperature. So iso just means the same. So we're going to hold at a specific temperature for a given amount of time to sinter what we do that. And then after that, again, there might be thermal stresses and various things that we need to get rid of, or we don't want to shock the system. So we may add an annealing step, and then there's cooling as well. And so all of these things can affect the ceramic part. So the heating and cooling rates, the temperatures we hold at, whether we do a burn off or not, all these things can affect the part on top of the sintering process. So just wanted to kind of illustrate that there's multiple things going on there. Okay, so now let's, I've kind of used the term sintering quite a bit, but I want you to think about what that means, and then before we start talking about it. So basically, see if you can describe what we mean by sintering, and then why it's done. And so obviously those two should be connected. So see if you can come up with kind of a definition, and then why we would do this sintering process. So you can obviously think about what it's like before sintering and what we're trying to achieve after sintering. So take a minute and see if you can come up with some answers to that. All right, so I put this video here on the front that you can kind of take a look at. This is basically a rapid sintering process done, but I put it up here as a kind of an interesting video to watch. A green ceramic part being sintered, and so I definitely encourage you to look at this video. It's very interesting, and it allows you to see a very quick snapshot of what's happening with the sintering process. But let's kind of get to a definition or what we're trying to achieve with sintering. So sintering is clearly a thermal process, right? And the idea is that we want to increase bonding, strength, and density of the material because we want to have a part that is one body, one continuous material, so not a collection of particles. So we want to increase bonding to do that, and that will increase strength. And for the most part, there are some applications where we want porosity, but for the most part, we're trying to increase density by removing porosity. And so all of those are connected. Strength and bonding will go up if there is less porosity. And so all of these are sort of connected. So oftentimes what we're trying to achieve with these, we're trying to achieve various microstructures to get these properties. So for the most part, we want to have high strength And so to get that, the best way is to have small grains, uniform structure, so small uniform grains, and then we want it to have, we want it to be flaw free. So that would be obviously great for that. We've talked about toughness before, so if we wanted to emphasize toughness, then we would actually want to get a duplex microstructure. So what we mean there is that we have two different sizes, and so that kind of emphasizes the crack deflection mechanism that we talked about. And if we had high aspect ratios, that would be like deflection or crack bridging, and so that would be good for toughness. If we want to have creep resistance, we really haven't talked about creep that much, but creep resistance is better when we have large grains and then we don't have any amorphous grain boundary phases, so glasses and so forth, because here we're using it at high temperatures. So we basically, the idea with creep is that we don't want it to deform at high temperatures, and so large grains are more stable, and then amorphous grains are unstable, and so we want to get rid of those. Oftentimes we're using ceramics for optical applications. So if we want transparency, we want to get pore free, so eliminate pores as much as possible, and then have grains that are either smaller or much larger than wavelengths, so that we have transparency. There's also some other applications, dielectric loss, myristor behavior, callus. All these have kind of unique microstructures that we're looking for. But for the most part, what we're going to try to emphasize is relatively small grains, uniform structure, and try to eliminate flaws and porosity as much as possible. That will give us kind of the best of most applications. Okay, so we start out before sintering with kind of the structure you see here in A. This is where we just have powder particles. So each one of these is a crystalline powder particle. And they're basically, again, just held together either with the binder or with van der Waals forces. So they're really not held together. And so if you touch or try to handle this part, it tends to break apart. So what we're going to try to do with the sintering process is we're going to try to join these particles together to form a homogeneous part that is one piece, not a collection of individual particles. And so how that is done is in the contact regions. So where these particles are touching, what we tend to see is a formation of a grain boundary, right? So now these are bonded together, right? There's a bonding happening when you have a grain boundary. And so the more and more grain boundaries we have, the stronger and stronger this is going to become. And so that's kind of the goal here, is that region that's touching becomes a grain boundary, and that grain boundary continues to grow, and these particles become closer and closer together, and we eliminate that empty space in between the particles, right? Therefore, increasing the density, increasing the strength, increasing the bonding that happens in this material. So those are grain boundaries growing. These are pores that are left over. Okay, so I want us just to think about this from a packing point of view. So we have particles. We've kind of represented them as spheres so far. If you think back to MSE401 or other intro courses where we talked about the maximum packing, right? We saw if we have evenly sized spheres, then FCC or HCP is the maximum packing we can have, and that's 74%, right? But in fact, we can have higher than that if we're not concerned with this uniform shaped. And so if everything doesn't have to be the same, we can actually even increase that, right? If we can get things to go into those interstitial sites, we could actually maximize that particle. So sometimes that can be good. Although I will warn, we talked about this already, when we have different sizes, that can result in sintering that is non-uniform. And so typically this is something to be avoided in most cases.